Good afternoon. Good afternoon. So good afternoon to all. So let's start the class now. Can you able to hear my voice? And can you able to see my screen? Am I visible and audible to all of you? Okay. Okay, fine. Just a second. Fine. So let's start the class today. Okay. So yesterday we have studied about the preparation of aldehydes and ketones, right? And today let's continue the class, and the physical properties also we have seen. Now let's recall the yesterday's class with a question. So can you name the reagents used in the Gatterman-Koch reaction? In this reaction, this is the Gatterman-Koch reaction, right? So which is used for the conversion of benzene to benzaldehyde. So here we used one reagent. So can anyone give me the reagents which is being used here? I'll give you 15 seconds. Okay, CuCl, only CuCl. CuCl is the one of the catalyst there. But the main reagent, who is the main reagent which is being used? Just think for a while and let me know in the chat box. Good. CO, carbon monoxide. What is the answer? Carbon monoxide with HCl and anhydrous AlCl3 with copper chloride. That's great, really great. So now let's move on to the next section. So today we are going to discuss about the structure of the carbonyl group and the chemical properties of aldehydes and ketones and uses of aldehydes and ketones. So we'll try to complete as much as we can. And moving on to the structure of the carbonyl group. So you can see the structure here. So what is carbonyl group? Basically, the C double bond O group containing compounds are called as carbonyl compounds, and the name of that group is called as carbonyl group. Okay. So you see here. So C double bond O is there. C double bond O is there. And in the one side, we have R group. And here in the structure, the other side also contains R group. So this structure represents the ketone. And if one of the R group is H, then it is called as aldehyde, right? So here you can see that is C double bond O R, and this can be R or it can be hydrogen. Okay. So first of all, we'll discuss about the number of sigma bonds present around this carbonyl carbon. So what are sigma bonds? Single bonds are called as sigma bonds, right? So here we have one sigma bond, and this is one C sigma bond, and here we are having double bond. In double bond, one is sigma, the other one is pi. Got it? So in carbon, single bond carbon, we have only sigma. In carbon double bond carbon, one is sigma, the other one is pi. In carbon triple bond carbon, one is sigma, the other two are pi. Got it? This is not only the case for carbon-carbon bond, for all atoms, this is the thing. So in the double bond, we have one sigma and one pi. So totally, how many sigma bonds we are having around this carbon? So 3 sigma bond we are having and 1 pi bond we are having. Sigma bonds are formed by the head-on overlapping of the orbitals, and pi bonds are formed by the lateral overlapping. That is the sideways overlapping of the orbitals. This you can see, right? You might have studied this overlapping concept and all in your chemical bonding lesson, no? So the same thing is here. This is about the sigma bond pi bond calculation. And moving to the hybridization of the carbonyl carbon. So you can see here, it is sp2 hybridized carbon. Since it contains double bond around it, so the hybridization of this carbon is sp2. Okay. And the double bond between the carbon and oxygen is shorter, stronger, and it is polarized. since it is the double bond, the length will be very small. So it is shorter. And bond length and bond strength is inversely proportional, no? So since bond length and bond strength are inversely proportional to each other, the bond is very strong and it gets polarized. Why does it get polarized? So oxygen is more electronegative than carbon, right? So oxygen gains the partially negative charge and carbon gains the partially positive charge. So we are getting plus minus poles. So it is polarized. Bond is getting polarized. And the carbonyl carbon acts as an electrophile, which is a Lewis acid, and carbon oxygen acts as nucleophile. Got it? Electrophiles are basically the Lewis acids. Electrophiles are positively charged species, and this carbon is the electrophilic center over there, and the oxygen is the nucleophilic center, which is negatively charged. Got it? So this oxygen is nucleophilic in nature. And this is the charge separation which is given. And the nucleophile prefers to attack the carbon, which is an electrophile. Okay. So based on this structure, we are going to see several chemical reactions which are associated with this carbon double bond oxygen system. Got it? Let's go with the first reaction in the chemical properties of aldehydes, that is nucleophilic addition reaction. We are going to see all these 6 reactions under this chemical properties. The first one is nucleophilic addition, second is reduction, third one is oxidation, fourth is reactions due to the acidity of alpha hydrogen, and under this we are going to discuss 3 reactions: iodoform, aldol condensation, and cross-aldol condensation. And the fifth one is Cannizzaro, and the 6th main reaction is electrophilic aromatic substitution reaction. Got it? Now moving on to the first reaction, which is the nucleophilic addition reaction. So you can see the mechanism here. So carbon double bond oxygen and R they are present. So this is the carbonyl system, and to this we are going to add the nucleophile. So nucleophile attacks the carbonyl carbon. Okay, nucleophile always attacks the electrophile. So it is attacking the carbonyl carbon, so that the double bond which is present there, it is moving, the electrons which is present in the double bond is moving to the oxygen, so that we get this intermediate. And this intermediate on hydrolysis, that is the reaction with H plus, forms, and this O minus goes and attacks this H plus, and we get OH here. So in the reactant, if you see, just now we have seen the hybridization of the central carbon is sp2. And after the addition of this nucleophile to the system, we are getting sp3 hybridization for the central carbon. So what is the geometry associated with sp3 hybridization? It is tetrahedral, right? So we are getting a tetrahedral intermediate over here. And then this on hydrolysis forms the tetrahedral product. Okay. Aldehydes are generally more reactive than ketones in the nucleophilic addition reactions. Why? Why aldehydes are more reactive for this reaction? So there are some reasons. So let's take the aldehyde first. So this is the aldehyde. One side R and the other side H we are having. And this is the ketone. Both the sides we are having RR group. Okay. Aldehydes are having the less hindrance. Why? In the other side, we are having only the small group called hydrogen. In the other side, we are having a little bit bulky group, R group. Okay, compared to hydrogen, alkyl groups are little bit big, no? So it is a bulky group. Whereas in case of ketone, you can see more electron deficiency at the carbon that I'll discuss now. In case of ketone, we are having both groups as alkyl group. Means 2 bulky groups we are having. Okay. So alkyl groups are electron donating group. In the first case, that is in case of aldehyde, we are having only 1 donating group. In case of ketone, we are having 2 electron donating group. So what happens after the donation? So when this alkyl group donates the electron to the carbonyl carbon, this carbon center becomes electron rich. It becomes electron rich. Okay, va? And this carbon is also becoming electron rich after the donation of electrons from the alkyl group. Okay. But while comparing the electron-rich capacity of both the aldehydes and ketones, since this ketone is having two electron donating system, ketones are ketone carbonyl carbon is more electron-rich compared to the aldehyde carbon. It is more electron-rich and this is less electron-rich. So there is an electron deficiency, more electron deficiency at the aldehyde carbon and less electron deficiency at the ketone carbon. Okay. So nucleophiles are already electron-rich species. Nucleophiles are electron-rich. And electron-rich cannot approach another electron-rich species more effectively, right? So which is more reactive? Aldehydes are more reactive compared to ketone. Got it? So do you have any doubt here in this reason? Aldehydes are more reactive than ketones due to two reasons. One is the steric reason, the other one is the electronic reason. Here we have studied the steric reason and also the electronic reason. Here more electrons are donated and there less electrons are donated. Got it? Is this clear to both of you? If it is clear, just type S so that I can understand. Okay, fine. Thank you. So now let's move on to some of the nucleophilic addition reaction. The previous slide talked about the mechanism of this nucleophilic addition reaction, and now we are going to see the real examples. Okay, first we are going to see the addition of HCN. So how we are going to add this HCN to the C double bond O system? First, this HCN reacts with OH minus present in the base, and it forms the nucleophile, CN nucleophile, strong nucleophile first. And then only the CN minus is going to get added to the C double bond O system. Got it? So cyanide is negatively charged species and that goes and attacks the positively charged carbon. Okay? And after this, we are getting a tetrahedral intermediate like this. And what is the next step? The second step is the hydrolysis step, no? So the O minus attacks the H plus and it forms a compound like this. Got it? The name of this compound is cyanohydrin. Why it is called as cyanohydrin? It contains cyanide group and an hydroxy group. OH group is called as hydroxy group. So it is called as cyanohydrin. Got it? You can add this easily. Just what you do, take the carbonyl system and to this we are going to add HCN. No? H plus and CN minus is the components. Just break one of the bond, add hydrogen to the oxygen and the nucleophile to the carbon. That's all. You will get the product. Got it? You will get the product. That is, we'll get OH here and CN here. This is what is the cyanohydrin given here. So these two are R and R dash. Got it? Just break the bond. Always add the positive part to the oxygen and the negative part to the carbon. You will get the final product. Okay. You don't have to follow these two steps unless and until they are asking you to find out the intermediate. You don't have to do this. If they are asking in the exam, if they are asking you to find out the product, just break the bond and add the components like this. You will get the product. Got it? Is this clear? We'll go for the second addition. That is the addition of sodium hydrogen sulfide NaHSO3. So this is the component. And what we can do, how this is getting separated, Na plus and HSO3 minus. So this is the plus and minus component of NaHSO3. Okay, so you can see here, NaOSO2H, which is nothing but a sodium hydrogen sulfide. The negative part goes to the carbon and the positive part goes to the oxygen. That is C double bond O we are having, breaking this bond, adding the positive part to oxygen and the negative part. Which is the negative part? HSO3 is the negative part, right? So adding this, we are getting. So why HSO3 is written like this? It is because always oxygen forms the bond with the carbon. That's why they have written the HSO3 like this. Sulfur will not go and form the bond with carbon, or hydrogen will not go and form the bond with carbon. Only oxygen forms the bond with the carbon. So that's why they have given in the materials like this. And this on proton transfer. So why proton transfer is happening? This is the proton transfer step actually. So in the proton transfer, this H plus proton is coming and forming the bond with hydrogen, oxygen, and this Na plus is transferred to the place of hydrogen. So this is called as proton transfer. Why this is happening means always oxygen tries to form the bond with hydrogen, not with any other positive component. It want themselves to be remain in neutral form. So that's why this is being happening. Okay. So proton transfer is happening, and on proton transfer we are getting hydrogen sulfide addition compound, which is crystalline in nature. Got it? So do you have any doubt here? You can write this step as proton transfer. The step is called as proton transfer. H plus is the proton, it is transferring. Is this clear to you all? Shall we move on to the next nucleophilic addition? If it is clear to you, just type yes, or it is clear. I am waiting for your response. Yes. Thank you, Ruchmita. We'll move on to the next addition. That is the addition of Grignard reagent. So what are Grignard reagents? Yesterday we have come across the same word Grignard reagent. No? What is Grignard reagent? RMGX is called as Grignard reagent. RMGX is called as Grignard reagent. We are going to add this RMGX to the C double bond O system. So what is the negative and positive part of this RMGX? So R is the negative part and MGX is the positive part. So what we have to do in the first step, break this bond, break this carbonyl bond, one of the carbonyl bond, add R to the carbon and MGX to the oxygen. So you will get the intermediate, tetrahedral intermediate like this. Okay. And this is in ionic form, right? It has to be neutral. So to attain the neutral form, this tetrahedral intermediate undergoes hydrolysis. That is, it is going to react with the water. On reaction with water, it forms the neutral product. Let me tell you how does it form the neutral product. In H2O, we have H plus and OH minus, right? So this OMG bond cleaves. And this H plus is going and forming the bond with oxygen and OH minus is added to the MgX. So you'll get the final product like this. And the MgX-OH is the byproduct. Got it? MgX-OH, MgX-OH will go out as the byproduct. Okay? So what we are getting from this? We are getting the secondary alcohol from this. What is the formula for secondary alcohol? CHOH. And two R groups are attached to it. If a compound contains CHOH, it is called as secondary alcohol, right? So initially we took an aldehyde. That is RCHO, and in the product part we got the secondary alcohol. In case of ketones, tertiary alcohols are formed. If you take ketone as a reactant, you will get the tertiary alcohol. So you can see here, both the groups are alkyl group, and addition of this RMGX with the hydrolysis, you can add water here. On a hydrolysis forms tertiary alcohol. You see, to this carbon, all the three groups are alkyl groups. So we are having only COH. So if a component has only COH, it is called as what? Tertiary alcohol. So what is the concept we are learning from this? Aldehyde with RMGX and H2O forms primary alcohol. Secondary alcohol. And ketone with the same reagent forms tertiary alcohol. So this is the concept you are learning from the addition of Grignard reagent. Whatever may be the reactant they are giving to you, just to follow this, you will get the answer. Okay? Is this clear? You can take down the notes or you can take the screenshot. If it is clear, we can move on to the next addition. Is the Grignard reagent addition clear to you all? Just type yes. Yes. Thank you so much. We'll go for the fourth addition, that is the addition of alcohols. So the formula for alcohol is ROH, right? So we are going to add this ROH component to the system. So ROH is called as alcohol. Addition of this alcohol in presence of HCl forms a compound. So how does and what is the use of this HCl? Dry HCl protonates the oxygen of the carbonyl group first. So that O minus is going and attacking the H of the HCl and forms the intermediate. That is that we are getting the hemiacetal from it. Or you can easily add this. What you do, just first we need to know the negative and positive part of the ROH, right? ROH. RO minus and H plus. This is how we have to separate. RO minus and H plus. Break the bond, add hydrogen to oxygen and OR to carbon. You will get this hemiacetal. You don't have to follow this mechanism at all. And you can just directly add the alcohol like this. You will get a hemiacetal. Okay. Since this compound contains only one OR group, it is called as hemiacetal. Then this hemiacetal on reaction with one more mole of ROH forms acetal. So why it is called as acetal? It contains two OR group. So it is called as acetal. So what is happening here? We are removing the H2O. We are removing the H2O from the component and we are adding this OR to the carbon which is present here. Carbonyl carbon. Okay. So first add the ROH to the aldehyde or ketone and then with one more mole of ROH, you remove one H2O and add the remaining OR to the system, you will get acetal. Got it? It is also called as gem dialkoxy compound. Gem dialkoxy. So OR is called as alkoxy. Since we are having two OR, it is called as dialkoxy. So why we are calling it as gem? Gem means geminal. Both the OR groups are attached to the same carbon, right? If a group is attached to, if two groups are attached to the same component, we call them as geminal compound. In haloalkanes and haloarenes lesson also, you would have come across this word. Geminal dihalides kind of thing would be there. The same thing is here. OR. Alkoxy is attached to the same carbon. So it is called as geminal dialkoxy compound. So similarly, ketones also react with alcohols to give ketones. So this is the aldehyde. Since we are reacting the alcohol with aldehyde, we are calling it as acetal. If we are taking ketone instead of aldehyde, you will arrive at ketones. Okay. Acetals and ketones are hydrolyzed with mineral acids, aqueous mineral acids to yield the corresponding aldehydes and ketones respectively. So you can see here the acetal or ketal is treated with H3O plus and it forms the hemiacetal again, and then this hemiacetal on treatment with H3O plus again forms the aldehyde or ketone back. Got it? It is a reversible reaction. So have you got it clear with the addition of alcohols part? It is clear, then we can move on to the next addition. That is the reaction with ammonia or the addition of ammonia and its derivatives. Okay. What is the formula for ammonia? What is the formula for ammonia? Ammonia is NH3, right? We can write NH3 like this, NH2 and H. So in case of ammonia, this hydrogen, yes, very good, Ruchinita. NH3 is the formula for ammonia. So this hydrogen is the Z group. And if it is some other component, we call them as the derivative of ammonia. That we'll discuss in the upcoming slides now. Okay. So basically, we are going to add ammonia and its derivatives to the carbonyl carbon. So how to add this? So who is the positive part and who is the negative part? NHZ is the negative part and H is the positive part. Okay. NHZ is the negative part and H is the positive part. After adding this and removal of water forms a compound which looks like this. So what you can do, you can directly get the compound final product by the removal of H2O in this manner. Just remove the water molecule and connect the nitrogen and erase it to the carbon. You will get the end product. This is the mechanism. Okay. Then we'll discuss one by one. First is the reaction with amine. So this is the formula for amine. So this is basically the primary amine. So what we have to do? Remove this H2O from this amine. Here Z is the R group, which is an alkyl group. So on removing the H2O molecule, we are arriving at a product called substituted imine. It is also called as Schiff's base. Substituted imine is also called as Schiff's base. Okay. Then is the reaction with hydroxylamine. What is the formula for hydroxylamine? NH2OH is hydroxylamine. And OH is the Z part here. So what we have to do now? Remove this H2O. So what we will get at the end? C double bond N OH plus H2O. So the name of this compound is oxine. If nitrogen is attached to an alkyl group, it is called as substituted imine. And if the nitrogen is attached to OH, it is called as oxine. Okay. We'll try to add some more compound. The third reaction is the reaction with hydrogen. What is the formula for hydrogen? NH2 single bond, NH2 is hydrogen. And this NH2 is the Ez component. Okay. So remove the H2O in the same manner and arrive at the final product. If nitrogen is attached to NH2, it is called as hydrazone. So from hydrogen, we are getting hydrazone. Okay. And the next addition is the reaction with phenyl hydrazine. So very good, Ruchnita. It is hydrazone. So next we are going to add phenyl hydrazine. So this is the compound, and what you do, you remove the H2O part. On removing this H2O forms phenyl hydrazone. Phenyl hydrazone. Very good, very good. That's great. Shall we move on to the next reaction? Okay, the next is the reaction with 2,4 dinitrophenylhydrazine. 2,4 dinitrophenylhydrazine is this, and the compound looks a little bit bigger, but the mechanism is same. Just you have to remove the water, H2O. What you will get? You will get 2,4 dinitrophenylhydrazone, which is an orange-red precipitate. So this compound is a colored compound, and the color is orange-red. Precipitate, it is forming as a precipitate. And this reaction is used for the test of the carbonyl group. So it is also called as 2,4 DNP test. That is 2,4 dinitrophenol test. Okay. If a compound contains C double bond O, only then we'll get this orange-red precipitate. Otherwise, we would not arrive at the orange-red precipitate. No. So if there is a color formation, that is orange-red color formation, then we can say that the reactant or the compound which we took initially has C double bond O. If you didn't get orange-red precipitate, then it is clear that the system doesn't contain the C double bond O. That is a carbonyl group. Okay. So it is used as a test to detect the carbonyl group present in the reaction mixture. Okay. So the sixth reaction is the reaction with semi-carbazide. So this is the formula of semi-carbazide. So what we have to do again? We have to remove the H2O from here, and finally we'll get the semi-carbazone from it. This is semi-carbazone. Okay. So is this clear to all of you? So we have discussed the nucleophilic addition reactions, and we have seen the mechanism, and we have seen some nucleophilic addition reactions over here. And at the last, in the reaction with ammonia and its derivatives, we have come across these 6 compounds addition. So do you have any doubt so far from the first chemical property of aldehydes and ketones, that is the nucleophilic addition reactions? If you don't have any doubt, just type it's clear, so that I'll move on to the next second chemical property of aldehydes and ketones. We got it clear? Clear? Good. So we'll go for the second reaction, that is the reduction of aldehydes and ketones. So what is reduction? Reduction is the removal of hydrogen. When we reduce aldehydes and ketones, we get alcohols. So the first is the reduction. Thank you. It is clear to 11th class students. Fine. So reduction to alcohols. So we have to use the reducing agents for this reduction purpose, right? So the first reducing agents that we are using here for the reduction of aldehydes and ketones is the hydrogen catalytic hydrogenation. That is, we are going to add the hydrogen in presence of catalysts like platinum, nickel, etc. So this is called as catalytic reduction. And the second reducing agent is sodium borohydride, which is represented as NaBH4. And the third reducing agent is lithium aluminium hydride, which is represented by the symbol LiAlH4. So these three are the reducing agents which are being used for the reduction purpose. Okay. First, we are going with the first reagent, that is catalytic reduction. We are going to reduce this now. So aldehydes are going to give alcohols. Usually, aldehydes on reduction for primary alcohol. Primary alcohol. You can see here CH2OH. So it is RCH2OH, right? So this is RCHO, and RCHO is giving RCH2OH, which is called as primary alcohol. Okay. Aldehydes always form primary alcohol and ketones always form secondary alcohol. Ketone on reduction forms secondary alcohol. Okay. We'll see an example. Before going to this example, I'll show you an example for the preparation of secondary alcohol from ketone. Suppose if I am taking RC double bond O and R. RC double bond O, R. It is not H, okay? RC double bond O, R. So this is a ketone. And ketone on reaction with H2 in presence of platinum metal or nickel metal, it forms secondary alcohol of formula RCHOH and R. So the C double bond O is getting converted to CHOH in case of ketone and forms the secondary system. Got it? Now let's go for the some other examples. So the reactant we took here is pent-3-enol. It is pent-3-enol. How to number this compound? You have to start from the aldehyde, right? 1, 2, 3, 4, 5. So 5 carbon containing system. So it is called as pent. And between 3 and 4 carbon, we are having an alkene double bond. So it is pent-3-ene. And in the first position, we are having an aldehyde. So it is called as enal. Okay. Pent-3-enal is taken as the reactant here. And this on treatment with H2 in presence of platinum. And then on treatment with lithium aluminium hydride. Forms two different compounds. First with the H2, it forms pent-1-ol. You see, it is pent-1-ol. That is, this hydrogen and platinum is reducing both the aldehyde part as well as the alkene part. Got it? Hydrogen is reducing both the aldehyde part and alkene part. But this lithium aluminium hydride, you see, it is able to reduce only the aldehyde part. Got it? Means lithium aluminium hydride and sodium borohydride cannot reduce double bond or triple bond. That is, it cannot reduce the multiple bond system. Got it? It can reduce only the aldehyde and the ketone carbonyl system. Is this clear? This is about the reduction of aldehydes and ketones. Is the reduction reaction clear to all of you? Just you have to remember the three reducing agents which are being used. Aldehydes gives primary alcohol and ketone gives secondary alcohol. And the last two reagents will not reduce. Thank you. It is clear to all of you. That's great. The last two reagents will not reduce the multiple bonds. It will reduce only the aldehyde and ketone. That's all. Just you take down the concepts alone. You don't need to memorize any of the reaction. Just take down the concept so that conceptual understanding is very important to crack all the competitive exams, right? Instead of memorizing the thing. So that if they are asking you any type of question, you can answer. If you memorize, you will not be able to answer. Just take down the concepts alone. Then second is the reduction to hydrocarbon. So what are hydrocarbons? Hydrogen and carbon containing compounds are called as hydrocarbons. There are 4 different types of hydrocarbons: alkanes, alkenes, alkynes, and aromatic hydrocarbon. So here we are going to see the reduction of our aldehydes and ketones to alkanes. Okay, you can see here the C double bond O is getting converted to CH2. C double bond O is getting converted to CH2. So this is the reduction part, and there are two naming reactions we are going to see under this. First one is Clemmensen reduction. Second one is Wolff-Kishner reduction. Moving on to the Clemmensen reduction, zinc amalgam and HCl are used in the Clemmensen reduction. So zinc amalgam is nothing but the zinc mercury part, and with HCl, the CO group is getting converted to CH2. Just note down this reagent alone. This is the Clemmensen reagent. And the reactant and product, the conversion is same for both. Just you need to remember the reagent alone for Clemmensen. Question can be of any type. They can ask you to find out the Clemmensen reagent, or they will give you the reactant product and you have to find out the reagent. So it can be of anything. If it is a Clemmensen reduction, then zinc amalgam and HCl is used. This is how you have to study. Okay. I think this is clear to you. There is no multi-step for this reaction. It is a single-step reaction. Got it? Shall we move on to the Wolff-Kishner reduction? Okay. In Wolff-Kishner reduction also, C double bond O is again getting converted to CH2. But instead of zinc amalgam and HCl, we are using NH2, NH2 and KOH. What is the name of this NH2, NH2? Just now in the reaction with the ammonia and its derivatives part, we have come across the name of this NH2, NH2, right? What is this? Can any of you let me know the name of NH2, NH2? Okay, let me know in the chat box later. Okay, so this is the Wolff-Kishner reduction. And now let's move on to the third one, that is the oxidation of aldehydes and ketones. Is the reduction part clear to you? Is the reduction part clear to you? If it is clear, just type S. It's very easy. CO is getting converted to CH2 with the Clemmensen reagent and Wolff-Kishner reagent. Yes, it's clear. Now the third is the oxidation of aldehydes and ketones. Aldehydes are easily oxidized to carboxylic acids on treatment with oxidizing agents like HNO3, KMNO4 in basic medium and K2Cr2O7 in acidic medium. So basically what you have to do, you have to take the aldehyde or the ketone and add one of the oxidizing agent to it. You will get carboxylic acid. That is the CHO part will be converted to COOH, carboxylic acid. Aldehydes on reduction forms alcohol. Aldehydes on oxidation forms carboxylic acid. Aldehydes on oxidation forms carboxylic acid. Okay. So, and ketones are generally oxidized under vigorous condition. That is, strong oxidizing agents only can oxidize the ketones, and also at elevated temperature. That is, at very high temperature and on using very strong oxidizing agents, we are arriving at the carboxylic acids from ketones. Okay. So, you can see this. This is an example for ketone. And what's the name of this ketone? 4 carbon we are having. So, it is called as butanone. And to this butanone, we are adding KMNO4, which is a strong oxidizing agent, potassium permanganate in basic medium. And it is forming the 2 different types of product. Okay, 2 product, but both are same in case of this reactant. So now, how we are getting this product? There are two carbon-carbon bond we are having. So we're having, this is carbon number 1, carbon number 2, carbon number 3, let's take. So now whether this bond, carbon number 1, 2 breaks or carbon 2, 3 breaks, that we have to find out, right? So for that you have to use one rule called Popov rule. So according to this rule, the rule states that the carbonyl group of the unsymmetrical ketone remains with the smaller alkyl group preferentially. So what does the rule says? In case of unsymmetrical ketone, the group tries to, just a second, okay, it tries to remain with the carbon which is very less bulky, okay, that is carbon number 2, 3 breaks. Carbon number 2, 3 break down. So here in case of the first alkyl part, we are having 2 carbon. And here we are having only 1 carbon. So which is a smaller alkyl group? So this is the smaller alkyl group, right? So that bond doesn't break. C double bond O tries to remain with the smaller alkyl group. So only carbon number 2, 3 breaks. And since this contains 2 carbon, one of the product is the 2 carbon containing acid, that is CH3COOH. And in the second part also we are having 2 carbon. That is first carbon is with CH3 and the second carbon is with C double bond O. So here from this we are getting 2 carbon containing acid, that is CH3COOH again. Got it? So we are getting 2 moles of CH3COOH from this particular reactant. If you are using some other reactant, we'll get the corresponding product according to it. Is this clear? Is oxidation clear to all of you? No? Okay, I'll give you an example. I'll give you an example to understand this. So I'll give you an example. It is CH3, CH2, CH2, C double bond O, CH3. So this is a ketone, right? So R, this is an R group and this is another R group. And this R group contains 3 carbon and this R group contains only 1 carbon. And this system with KMNO4 or on oxidation is now going to form 2 different carboxylic acid. One is A and the another one is B we can take. Okay. Now which bond has to be broken? Whether this bond or this bond. Obviously, the more number of carbon containing alkyl group will get break. Okay, what this bond breaks down and this part is going to form the 2 carbon containing carboxylic acid, that is CH3COOH, since the part contains 2 carbon. And here we are having 3 carbon, no? Those 3 carbon will form the another carboxylic acid, that is CH3CH2COOH, 3 carbon containing carboxylic acid. So one is the ethanoic acid, the other one is the propanoic acid. Is this clear now? The C double bond O group tries to remain with the smaller alkyl group. So basically both are going to form the carboxylic acid, only the carbon number remains different. Got it now? Yes, you got it clear. Then I think let's move on to the remaining thing. Next part. The next oxidation is the mild oxidizing agents like Tollens reagent and Fehling solution can oxidize only aldehydes. So hence it is used for the test of aldehydes. So we are going to see 2 more reactions, that is Tollens reagent reaction and Fehling solution reaction. Both the reactions are used for the test of aldehydes. So let's see one by one. The first is Tollens test, which is also called as silver mirror test. So in this test, ammoniacal solution of silver nitrate is being used as the reagent. So who is that reagent? You can see ammoniacal. This part is the ammoniacal silver nitrate. This is the Tollens reagent. And if you add the aldehydes to the tolerance reagent, aldehyde is getting oxidized to carboxylate ion, which you can see here. This is called as carboxylate ion. We can take this as carboxylic acid also. So basically oxidation occurs. And Ag is coming out, which is the silver mirror, and NH3 and H2O are the byproduct. Okay, Ag is formed as a silver mirror. Suppose if you are doing the reaction in the test tube, we are taking the ammoniacal silver nitrate solution in the test tube first, and we are adding the aldehyde into the tolerance reagent. And after adding this, we can able to see a silver mirror kind of layer which is formed at the walls of the test tube. You can see in the picture, I think. Is that clear? That silver mirror kind of thing? I think it's clear. If you couldn't find out, yeah, if you couldn't see the silver mirror layer kind of thing forming at the walls of the test tube, then you can come to the conclusion that the solution or the reactant doesn't contain aldehyde group. So there is some other functional group present in the system, and that's why silver mirror is not being formed. So like this, they are using this test as a test for aldehydes. Okay. Both aliphatic and aromatic aldehydes gives tolerance test. Aliphatic means all methanol, ethanol, propanol, and in case of aromatic aldehyde, you can take benzaldehyde. So both the aliphatic and aromatic system respond to this test. Okay, we can go for the next solution, that is Felling's solution test. So for Felling's solution, we have to take two beakers, that is we have to take two solution. One is Felling's solution A, that is copper sulfate, and Felling's solution B is the alkaline solution of sodium potassium tartarate. That sodium potassium tartarate alkaline solution is also called as Rochel's salt. And we are going to mix these two solutions first. Okay, what we are going to do? We are going to mix these two solutions, Felling solution A and Felling solution B. They are now going to mix with each other. And in this mixed solution, we are going to add our aldehyde. Okay, to this solution. So this is the Felling solution. To this solution, we are going to add the aldehyde. If you are adding the aldehyde, this forms carboxylate ion again, or you can take this as carboxylic acid. Means aldehyde is getting oxidized to carboxylic acid with the release of Cu2O and H2O. So how to find out whether aldehyde has got oxidized or not? Just by seeing the thing. The deep blue color complex of this Felling solution will be converted to red-brown. You will get a red-brown kind of precipitate or solution in your test tube. If you get the red-brown color at the end, then you can conclude that the aldehyde has got to oxidized. If you then find out red-brown precipitate in your test tube, then you can conclude that the system doesn't contain aldehyde in it. But only aromatic aldehydes do not respond to this test. Only aliphatic respond to this test. If you are having benzaldehyde in your compound, then in that case also you will not arrive at the red-brown precipitate, because only aliphatic aldehydes respond to this test. Okay, so it is very important. For tolerance, both aromatic and aliphatic respond, but for Felling, only aromatic aldehydes respond to this test. You can get some statement type of question from this concept. Okay, or they will ask you to find out the ammoniacal silver nitrate and the Felling solution formula from the given option. Okay, so such kind of questions you can get from here. So is this clear? Is this clear to all of you? So let me summarize the thing which we have seen so far. We have seen three reactions. The first one is nucleophilic addition reaction. This is the mechanism. And second one, we have seen reduction, catalytic reduction we have seen. That is a conversion of C double bond O to CH2OH. And in Clemmensen reduction also we have seen zinc amalgam and HCl. And Wolff-Kishner reduction also we have seen. The third one is the oxidation reaction. So oxidizing agents are basically KMNO4. Yeah, Ruchinita, I'll tell you, I'll teach you the tolerance once again. Let me conclude it, okay? So CHO is getting converted to COOH on reaction with KMNO4, potassium permanganate, nitric acid, and potassium dichromate, etc. Yeah, K2Cr2O7, that is potassium dichromate. Good. And tolerance test. So what is tolerance test? The reaction of aliphatic or aromatic aldehydes with ammoniacal silver nitrate solution is called as tolerance test. So this test is used to find out whether the reactant contains aldehyde or not. If a reactant contains aldehyde, then at the end of the reaction, the silver mirror is formed at the surface of the test tube or the container which you are using. If you don't find any silver mirror kind of thing, then you can justify or come to the conclusion that the system doesn't contain aldehyde. Got it? Ruchinita, is this clear to you? So the chemistry that is being involved here in this reaction is oxidation. Aldehyde is getting oxidized to carboxylic acid. Clear to you, Ruchinita? Yeah, it is clear. So now next we have seen Fehling solution test, and in Fehling solution we took copper metal ion and OH minus ion, which is a deep blue colored complex. And if the system contains aliphatic aldehyde, the deep blue color will be converted to red brown. And if it contains some aromatic or some other component, color formation, red brown color formation, that is due to the presence of formation of copper oxide, will not be seen. Okay. So this is what we have discussed so far. The fourth reaction is reactions due to acidity of alpha hydrogen, that we can discuss in the next class. Okay. So do you have any doubts from the part which we have seen today? Yeah, questions. So if time is up, so we can solve the questions in the next class. Okay. I'll give you the questions in the next class. So any more doubts you have? Okay, then we'll wind up the class for today. Thank you. Thank you, students. Thank you so much for, no doubt. Okay, that's fine. That's great. You go and study. We'll continue this on next Monday. Okay, thank you. Thank you, students. Thank you so much for your attention.